Hello. The topic of this lecturette, or a short lecture, are number systems. What is a number system? Number system is a way in which numbers are named, written, notated, written. Okay, so this is the way in which we represent numbers. Historically, there was many different number systems. In this lecture, we will only talk about so-called positional number systems. And the examples of these positional number systems are the decimal system that we use nearly every day, binary system, which is the most important number system from the point of view of construction of computers, and also other two number systems quite often used by programmers, much less frequently used in everyday life, and this will be octal and hexadecimal system. Let's start from the most obvious, the decimal system. This is an example of a decimal number. It is 24,356 and 782,000. The reason why the decimal system is called positional is that each digit has its numeric weight, which is attached to its position within the number. From the decimal point, moving to the right, these weights are 1, 10, 100, 1000, 10,000. Then we would have 100,000, million, and so on. And to the right side of the decimal point, we have 1/10, 100, 1000, and so on. Looking closely at these weights, you can notice that all these numbers are powers of the number 10. So, for example, 1 is 10 raised to the power 0. Just as a reminder, any number raised to the power 0 is 1. 10 to the power 1 is 10. 10 to the power 2 is 10 times 10, it's 100. And then 10 to the power 3, 1000, and so on. Similarly, the fractional weights, 10 to the power minus 1 is 1 over 10, 1/10. 10 to the power minus 2 is 100, and so on. We can now give individual names to each of the digits, and these names will follow the power number next to the weights. So this digit will be called x4, x3, x2, x1, x0, and so on. At this position, we can try to write a formula showing the value of the whole number based on the values of the individual digits. And it will look something like that. The first digit is 2, and its weight is 10 to the power 4. So we have 2 times 10 to the power 4. Plus the second digit is 4 times 10 to the power 3. Then 3 times 10 to the power 2, 5 times 10 to the power 1, 6 times 10 to the power 0, 7 times 10 to the power minus 1, 8 times 10 to the power minus 2, 2 times 10 to the power minus 3. In the next step, we will replace the actual values of the digits with these names that we given previously, so x4 times 10 to the power 4, and so on. This creates a kind of a generic formula, but we can go even a step further and present the same formula in this form, in which the number n represents how many digits on the left side of decimal point, and the number m represents how many digits on the right side of decimal point. You can notice that the left-hand side digits are numbered from 0 to n minus 1. It's important that it is n minus 1 because if we have n digits but we start counting from 0, then the last digit in this count will be n minus 1, definitely not n. So we have n digits on the left side, m digits on the right side, and each individual component in this long sum will always have x with some index times 10 to the power with the same value as the index next to x. We can use this observation to provide the ultimate formula for the decimal system notation, which looks like this. The big symbol is the Greek letter sigma, and sigma is just a big Greek S like sum. So this symbol represents a sum of components. Each of these components is built like in this formula here, xi times 10 to the power I. And this I will change across various components of this sum, starting from minus m to n minus 1. So basically this formula is the exact equivalent of this longer formula. Just mathematicians prefer this form because it's much concise and you don't have to use the ugly multiple dots like here and here. This makes the ultimate formula for the positional system with the base b equals 10, which is called the decimal system. Once we have this formula, we can create another formula to define the binary system, which is built on the same basis as the decimal system. The only difference is that the base equals 2. Therefore, the powers of 2, or the weights for consecutive digits, will be like 1, 2, 4, 8, 16, 32, 64, and so on. These are powers of the number 2. Another popular system is a hexadecimal system with the base equal to 16 and powers like 1, 16, 256, 4096, 65,536, and so on. And the last that we will discuss today is the octal system with the base equals 8. The final formula in this page is the generic formula for any positional system, which uses the same maths as previously, but we don't specify any particular base, we just say any base b. So in practical use, we have bases like 10, 2, 16, and 8, but mathematically it is possible to create a positional system based on any other number. So let's have a closer look into the binary system. This is an example of a binary number, 10111.101. This dot here, the symbol here, would be technically called binary point. Now, not decimal point, but this is just a small detail. How to read something like that? Similarly to other positional systems, each digit in this binary number has its value based on consecutive powers of number 2. So these powers are 1, 2, 4, 8, 16, and so on. And the other way around, it's 1 over 2, 1 over 4, 1 over 8. So how to read this particular number? Something like this, 16, because we have 1 on the position worth 16. Then, why don't we have 8 here? Well, we don't have 8 because there is a 0 at the position 8 in this number. But we have a 1 at the position 4, a 1 at the position 2, and another 1 at the position 1. And then we have 1 over 2 and 1 over 8. We just need to sum up all these numbers. It gives 23 and 5/8, or 23.625. That's the decimal representation of our binary system number. Okay, if you read it like there are 10 categories of people, the joke won't work. Okay? Important fact about binary system is that the number you can see here on the screen, it's not 10 anymore. 10 is a decimal value in decimal system. Binary, it's 10. So there are 10 categories of people, those who understand binary and those who don't. But actually, why anybody would like to understand binary? Binary is very impractical. Binary numbers are terribly long. They are a mishmash of ones and zeros, terribly difficult to remember, terribly difficult to write down. So why? The only answer is because computers use binary numbers. Next question. Why do the computers use binary numbers? And the answer for this question is right here. Because 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, 1 plus 1 equals 1, 0. That's everything that you need to know about addition in binary system. Okay? If you compare it with decimal addition with single digits, 5 plus 7, okay, 12, 7 plus 9, 16, and so on, so much complicacy. And here, just 4 elementary operations cover every aspect of adding 2 single-digit binary numbers. How we can make it into working addition of any length binary numbers? Very simply. We have 3 examples here. So let's have a look at these additions. 1001 plus 0110. We will add consecutive digits starting from the right hand side. It's very important that we always start from the right end of a number. It's the same thing whether it is a binary or decimal. You always should start addition from the right hand side and proceed to the left. So 1 plus 0 is 1. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 0 is 1. The result is 1, 1, 1, 1. Simple? Okay, let's take a little bit more tricky example. 1 plus 0 is 1. 1 plus 1 is 1, 0. Oh, attention please, 1, 0. We cannot put 1, 0 into a single digit position. So we will put 0 and we will carry over additional 1 to the next position of our addition. So now we have 1 which was carried over from the previous addition, plus 0 plus 0, 1 plus 0 plus 0, it's 1. 1 plus 1, again it's 1, 0, which we could just put here as 1, 0, or more correctly, more technically correct, I will put 0 here and use a carryover to put an additional 1 here. Following number, 1 plus 0 equals 1, 0 plus 1 equals 1, 1 plus 1 is 0 carry over 1, but with this carry over 1 I have 1 and 0. It's together 1, 0, so I put 0 once again and carry over 1. And the final one, if the final addition, 1 plus 1 is 0 carry over 1, but I have 1 and 1, it's again 0 carry over 1, and the 1 from the carryover plus 1 plus 0, it's 1 plus 1, it's 0 carry over 1, and 1 goes here. The result is 1, 0, 0, 0. I will stop here for a couple of seconds to give you a chance to look at these numbers and find the decimal representations of these numbers. and finding out that what we have calculated is a really correct value. So taking the first addition, 1001, if you remember 4 consecutive powers of 2, so the right hand side 1 is has value 1, 2, 4, 8, so there is 1 and 8, so this is 9, and the other number is 1, 2, 4, 8, so it's 2 plus 4, 6, so this is 9 plus 6, it should be 15, and this binary number down here indeed is 15 because it has 1, 2, 4, 8, 1 plus 2 is 3, plus 4 is 7, plus 8 is 15, everything works, okay? Binary system works. So that's one good reason for computers to use binary system. But also, I'm sure you have to remember when you were memorizing timetables at school, probably primary school, many years ago. 6 times 7, 42. 6 times 6, 36. 7 times 8, 56. 9 times 9, 81. Terrible thing. I will show you timetables in the binary system. Binary times table. 0 times 0 is 0. 0 times 1 is 0 as well. 1 times 0 is 0. 1 times 1 is 1. Complete times table for single-digit binary numbers. I will not discuss these three operations here. This is a notation of written binary multiplication, but it's quite complex and it's not essential for us, for game programmers. So if anyone would be really interested how you can use binary system to multiply numbers, that's the way how to do it. But I will leave this part without a comment. Contact me if you would like to hear more about this. Let's go to the final slide in this presentation, review of number systems. So here in front of you there is a table showing numbers from 0 to 15 in decimal code. So the first column is decimal, the second column is its binary representation, then octal representation, and hexadecimal representation. We'll be talking more about the binary representation and sequences of binary numbers in the next lesson, in the next lecture, so I will leave it for a moment. But let's have a look at the octal representation. 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7. And then in octal representation, we just have digits from 0 to 7. Okay, there is no digit 8. So the decimal value 8 is replaced by 1, 0. How to read 1, 0? 1 stands for number of 8s in the number, and 0 is the number of units. So 1, 0 is 8. 1, 1 is 9, 1, 2, and so on, so on, so on. The hexadecimal system, which will be also discussed next time in the next lecture, has as many as 16 digits, and these digits represent numbers, decimal numbers from 0 up to 15. Of course, this means that when we exceed the digit 9, we run out of decimal digits. Therefore, in the notation we use for the hexadecimal numbers, we use additional 6 digits, A, B, C, D, E, and F, for consecutively 10, 11, 12, 13, 14, 15. And on the right-hand side, you have, just for your practice and comparative work, binary representation of the same numbers. It's a decimal 255 and 168 65, in binary, hexadecimal, octal representation, and also in many programming languages. When you type 165, the compiler, the interpreter, will automatically consider this a decimal numerical value. But if you provide a prefix, so additional symbols like 0x usually will be interpreted in languages like C, C++, C#, Java, JavaScript, will be interpreted as the hexadecimal value. So 0xA5, this is hexadecimal A5. And if you just add a 0 in front of a typical decimal number, these languages will consider this an octal representation. So you have to be very careful here, because in mathematics, a notation like this 0245 would be just 245 decimal. But in a programming language, this will be, because of the zero, the leading zero or prefix zero, as we call it, this will be automatically considered an octal number, so it's octal 245. So 2 times 64, 64 is the second power of 8, 2 times 64 is 128, plus 4 times 8, plus 5, this is actually the number 165 decimally. Thank you very much. Next time we will be talking about binary representations of negative numbers. Today we were only discussing positive numbers, and possibly you know how to represent a 0, but we were not talking about negative numbers. So this will be done next time. Thank you very much.